Okay, so you've got this reaction going, right? You've got this boiling flask with your hexene, and then you're slowly adding iodine to it over the course of time, and you're allowing this reaction to go forward. And the book is going to tell you, let the reaction go for a certain amount of time, and then you're keeping an eye on the color. So is the color getting lighter and lighter? And if it is, then that's a very good indication that the reaction is continuing on for you. So we need to talk about what to do next. After this reaction time is over, what are we doing? Well, before we do that, the purpose of the condenser is just like it was in any of the other labs that you've used a condenser. This could generate some vapor. That vapor could go up and out because we're generating some heat, right? And we don't want to lose any of that vapor. That could be the compound that we need to capture, so our percent yields are going to be very, very good at the end. Well, in order to condense those vapors down, we use a condenser. That's the purpose of it. So water goes in from the bottom and water goes out of the top. And that will cool those vapors down, and it will trickle those back down into the boiling flask where they need to be. All right? Okay, so with that said, what's the next part of the reaction? Well, I'm going to take the boiling flask, and this boiling flask now is going to be off, and there's going to be a solution on the inside, and that solution is going to have another reaction. So the reason that we do this next step is that sodium borohydride that's present, NaBH4. There could be some extra of this that's left over. And we don't want any of that extra sodium borohydride to interfere from this point of the reaction and into our product formation. So we want to get rid of all of that extra. And the way that we get rid of it is very easy. We add a little bit of water. That's all that we have to do. So the lab directions are going to tell you to add a certain amount of water to the boiling flask. And the reason for that is not to make things weaker. The reason for that is to destroy any of the sodium borohydride that might be present that's still lingering around. Okay? So, after you add the water, you might see a little bit of bubbles that begin to happen. So, those bubbles are a very good sign. The bubbles means that the sodium borohydride is reacting with the water, and we are getting some liberation of some gas. And that gas is going to be H2, hydrogen, because that H2 is coming from the sodium borohydride that's being broken down. Okay? So, water kills out sodium borohydride. We don't want any of that left over in the flask. We want to convert that completely into something that can escape and basically be present without interfering with anything else. Not only that, but the next step is also going to concern you adding hydrogen peroxide, H2O2. Hydrogen peroxide. Well, this is not your hydrogen peroxide from the store. Your hydrogen peroxide from the store is a 3%. We don't use 3% in the lab mostly. What we do use, however, and what this lab requires, is a 30%, 10 times as strong. You need to be very careful with the peroxide that we use in the lab. And the reason is because that 30%, it loves water, and it loves to extract water, especially from your skin. So if you put some of the peroxide onto your finger or your hand or your arm and you leave it there, it will absorb the water from that spot and you will be left with a white blemish that will be on your skin. The way that you can fix that, put some lotion on it. Make sure it stays hydrated. Make sure it stays wet. And that dry skin can go back to moisture skin after the fact. All right, so that hydrogen peroxide, it's also very explosive. You don't really want to get this near some heat. You really don't want to get this near an open flame. This thing can heat up. It can generate bubbles. It can generate pressure. It can explode. It can do a whole series of different things, not only dehydrate, but blow up in your face at the same time. Not sodium, but hydrogen peroxide can also be found in acne creams. Peroxide or a sodium-based peroxide are traditionally found in these products. They're not at 30% though, but they are higher than 3% that you would find out onto the consumer shelf. And the reason for that is because it dehydrates. It gets rid and it kills the bacteria. And that is what helps your pimples and your acne go away sometimes. So those peroxide-based consumer products are out there for a reason, and that's why. All right. So it's going to tell you to slowly add the peroxide and water to the flask. You're going to see some bubbles that are going to be liberated and generated. It's going to say do this kind of drop by drop at a certain point. Allow the reaction to continue. The reaction's probably going to get a little hot. The boiling flask you're probably not going to be able to hold. And that's just, again, a sign that the reaction is going forward like it needs to be. So that's going to be the next step of the reaction itself. Okay? After you do that, you're then going to go through a process of determining or separating your organic. So the separation process I'm not going to explain. And the separation process can be found in your lab book. And the reason that I'm not going to explain it is because this is your basic separation that you've always done, really, in all of the other labs this semester. So no big deals here. No big issues at all. It's, the same stuff over and over and over and over and over. But leading up to this point, there's some things that you have tackled or that you will tackle that's different than what some of these other labs have presented. All the way from the setup to the reflux, to the slow addition of adding the reagent, to the bubbling, to the peroxide. All of this is new, but the separation is not. Okay? So, after you separate your product, you're then going to determine if your product is one of two different ones that's in the scenario. What begins to happen here, what we want to look for, is that we know that this is hexane. 1, 2, 3, 4, 5, and 6. And we know that a double bond is on the first carbon. Well, when this reaction happens, the particular reagents that we're adding here, so the reagents again are sodium borohydride, water, and peroxide. The iodine and THF, they're not going to play a matter. That's just like a catalyst. Those things are present to make the reaction speed up and to go quicker, but the iodine and the THF, it has nothing to do with the final product at all. These are the major reactants that are going forward. The only thing that this combination does is it adds an OH. That's it, folks. It adds an OH. And it's our job to figure out where the OH is added. So, what do I mean by that? Well, if I look at that double bond, I know that that double bond is going to break. And when that double bond breaks, I'm going to get a side of attachment here and a side of attachment there. I can draw them both up if I want to. No big deal. Whatever. Well, one of these is going to get an H, and the other one is going to get an OH. Where would that H and OH come from? Ta-da! Right here. There's your water molecule, HOH. So the object of the game here is to figure out if my H goes there and the OH goes on the inside carbon, or 1, 2, 3, 4, 5, and 6, two sites of attachment, my OH goes here and my hydrogen goes there. Those are two different products that could form. It's up to me to figure out which one it is. That's the major product. I know that both of these will probably happen. I know that both of these will be in my boiling flask, but this will allow me to separate one from the other. And I'm going to have to figure out which one is the major product, which one is showing up in the most amount. All right, well, we have names for these. This is a 6-carbon chain, so this is called hex, and it is an all single bond. Now, the product is at least. So this would be a hexane. Hexane, right? The same thing's going to happen down here at the bottom. I've got 6 carbons in total. That's called hex, and it's a hexane because they're all single bonds. However, we have an OH group. And this OH group, if you've looked at other labs before already at this point, an OH group is an alcohol group. And that alcohol ends in OL. So what do we do in the name? Well, we make that present. So instead of hexane, we call this hexanol. That OL represents that there is an alcohol on the molecule. The same thing happens down here at the bottom. It's just in a different location. It's still an alcohol, so hexanol is still the name for that. Now, there's got to be a difference between these two hexanols, and that's where the first part of the name comes from. Just like 1-hexene, the 1 told me where the OH group was attached. The same thing's going to happen here. This is 1-hexanol, meaning that the OH group is attached to the very first carbon. So 1-hexanol for that reason. The same thing happens down here at the bottom. This is my carbon number 1. This is carbon number 2 in line. So this would be a 2-hexanol for that reason. All right? So it's up to you to figure out which one of these you have made in the lab. After you go through this reaction, after you go through adding these reagents, you're going to get a product. This product is going to have to be identified, and you're going to have to identify it as 1-hexanol or 2-hexanol. Now, how do you do that? Well, the easiest way, number 1, is to use FTIR. And you're going to look at the spectrum. The spectrums are slightly different. And use our database. The database will tell you what product is found or what product is present. The formula weights. Well, the problem here is the formula weights are the same. So we can't really use that as a judgment, but we can use FTIR. As far as density goes, this is the same compound. It just has an OH in a different location. Same number of carbon, same number of hydrogen, same number of everything. Because of that, density is going to be the same, or they're too close to distinguish apart. So we can't use the density or the density meter in order to determine the difference here. The melting points. The melting points for both of these are in the negatives. It's -50, give or take a little. So this is unobtainable in our lab. We can't really use a melting point because this stuff's a liquid. We're going to end up with a liquid product here, not a solid product. So because of that, we can't do a melting point. However, because it's a liquid, if we can't do melting point, then maybe we can do boiling point. And this is going to be the way that we can determine which one that we've made. Because the boiling point for 1-hexanol is different than the boiling point for 2-hexanol. I know that they have the same number of carbon, the same number of oxygen, the same number of hydrogen. However, the OH locations are different, and that's what allows the boiling points to be different. 1-hexanol is 157 degrees, and 2-hexanol is 140 degrees. Why? Well, 1, 2, 3, 4, 5, and 6. I have an OH group on the first carbon. This is a very long linear molecule. And if you watched other videos up to this point, maybe you've stumbled across the one where we talk about boiling points and how the structure relates to those boiling points. The more branched that they are, the more things that hang off of the main chain, the lower the boiling point gets. Well, this one is not really branched. It can all form basically a big long straight line without a problem. So that's 1-hexanol. Now, the issue with 2-hexanol, 1, 2, 3, 4, 5, 6, is that this is the longest continuous chain right there. And then off of this carbon, I'm going to have an OH that kind of points up. Well, that functional group, that molecule that's branched, these things cannot stack together as well. It's like stacking books. Stacking books, that's okay with very flat molecules. But imagine you've got those 3-ring bonders. And imagine you trying to stack those 3-ring bonders all in the same way, all up a big old long tower. They're going to fall over. They're not going to stack very well. The same thing happens here with 2-hexanol. The molecules do not stack. Therefore, the boiling point is lower than the 1-hexanol. All right? So you're going to do a boiling point analysis, and that boiling point analysis is going to kind of give you an idea of which one that you've made. So, what are the thresholds here? Well, number 1, you want to make sure that you make an alcohol. Number 2, you want to make sure that your percent yield is greater than 60. And number 3, you want to make sure that you ID this product correctly. So that's the object of this lab, or those are the objects of this lab. And I think that if you take very careful steps, very careful measures in the separation process, I think that you'll meet all 3 of these without a problem. So 60% yield, it's a good indication that this reaction goes specifically in one way. Not completely, but we're giving you the benefit of the doubt, and we're giving you 40% wiggle room that you can mess up. So I think that you'll be able to obtain the percent yield without a problem. All right? So that's the lab in a nutshell for the Markovnikov. And hopefully now you can walk away from this lab and understand what Markovnikov is, what it's basically trying to tell you, and if everything follows Markovnikov's rule. So good luck. Come at us with questions when you need us. We'll be there.